All right, I guess we'll do the OSD transactions here as we're nearing the end. So, Sage, you want to run through this one?
Sure. Sam, are you around? Let's see, Josh, you're here.
Can you hear me?
Yep.
Yep.
All right, cool.
Can you hear me?
Yep.
Excellent.
All right, so this one is born mostly out of frustration of implementing sort of the same set of two-phase commit type updates on top of Rados. Because every time you do it, you have to have some sort of cleanup mechanism. The first one was in the file system. That one ended up being actually not that complicated though, because basically everything in CephFS goes through the MDS journals, and then we are very careful to like keep things in the journal for a really long time, and so we very lazily sort of expire stuff. So there's sort of an implicit two-phase type operation in that. That's just totally fine. But in the case of RBD, things are mostly better. But in RGW, there are lots of cases where you have objects that are written somewhere in Rados, and you have some sort of metadata that points to it or references it, or in some other way that you need to update atomically. And it's just frustrating every time you have to do that to reinvent your own two-phase commit thing. So the basic idea is to expose a multi-object transaction to Librados. My hope is that we could do this in a really generic way. So we already have this object write operation type in Rados that's a set of operations to atomically apply to a single object. So the idea would just be to literally take n of those, map to a bunch of different objects, and then the client would specify which one is going to be sort of the coordinator master. And then you would send the operation to the primary, and the primary would make sure that it all gets applied atomically and give you an ACK when it's done. There are a few different variations on how this would actually get done. The one that makes the most sense that we've discussed recently is listed as model 2 here. So in the blueprint. So the basic idea would be you'd send this full transaction to the master. It would just hold that in memory for the duration. It would send a prepare to any of the slaves that have just their portion of the update, just their subpart of that object write operation. The slaves would apply those, not to the actual object, but they would sort of write them aside in some place that doesn't touch the object yet, so they can roll back safely. But once it's durably recorded on their disk, they would reply with an ACK back to the master coordinator. The master would, once it gets all those ACKs, it would apply the transaction locally and mark it that it's committing. And then it would send an ACK to the client, because at that point we're committed. And it would also send messages to all the slaves again saying that they should take that thing that they durably prepared and apply it to the actual object. And once the slaves act, then the master could discard its sort of committing state, and everything would be all done. So the key thing that doing this in Rados buys you is that all of the failure paths rollback stuff can be handled by the OCs themselves. They can communicate with each other. So for example, if there's a peering shift, then when we reactivate, we just look at our PG state and we say, do we have slave operations that we've prepared but haven't committed yet? And if so, we'll just tell the master. We'll ask the master if we should roll them forward or roll them back. And the master can do that. We don't really have to do the same thing on the master, because if there's a peering change and the master primary moves to a different OSD, the client's going to resend the whole transaction anyway, just like it does every other operation. So there's not really any point in. That's the reason why the master holds the transaction in memory and doesn't write it to disk, at least in this current formulation. On the email list, you might have noticed Lee proposed sort of a different one where it did record it and some other stuff happened. And I think they both kind of work. Mostly it's just a matter of trying to minimize the number of writes we do and keeping it as simple as possible. Right. So any questions so far? I think in general you would.
Who coordinates cleanup after a? That's the reason for persisting the original transaction, I think.
Who coordinates cleanup after which?
Okay, so let's say we get to part or bullet point 3. 3 of the slaves have persisted the repairs, 3 of them haven't. And everyone goes through a pairing change. When we come back up, 3 of them have uncompleted transactions, and the other 3 don't. Who decides that this is a rollback situation and not a roll forward?
The ones that have prepared. Well, the ones who don't have it prepared don't know anything, and so they don't do anything. The ones that have it prepared will send a notify to the master object. The master object won't have it in memory because it also went
the
from
primary. The primary didn't prepare. Okay.
Yeah, and it would just send a rollback because
no, the primary doesn't necessarily have it in memory, but he'll say he doesn't, and it'll send a rollback. Yeah. Okay, that makes sense.
Exactly. Yeah. Yep. Yeah. So one suggestion here was that you might delay the rollback because it might be that the client resends the same transaction momentarily, but that's sort of an optimization. You can worry about that later. It's probably simpler just to, if you like. Yep. So that keeps that part pretty simple.
It does seem like this works.
It does work. Yeah.
Well,
so there are lots of ways that we can make it slightly more complicated and more interesting. For example, each of those object write operations could potentially have read guards at the front, like make sure that the version is X and call some class operation or whatever it is. And if those fail, then the prepare would fail basically, and then the transaction would abort. So that's one sort of easy extension. And RGW might use this, for example, to make sure that we don't go over quota or something on the index or something. I don't know, whatever it is. I can imagine lots of uses there. I probably wouldn't worry about it in sort of the first iteration. Although we just want to make sure that we adequately test all the prepare back failures, I guess.
Well, if it's a generic object write operation, then they can fail. So actually, we probably do have to handle it. That's easy though. I mean, it's just that if you get through prepare transaction and you get an error code, then you send a fail, and that's it.
Yeah. Yeah,
it's actually kind of tidy. I thought it would be more complicated.
When I think about this, the struct here at the top, where it's just a map of existing object write operations, I think it just works, but I'm sort of expect that we're missing something, and it's not that simple. But probably won't find out until we actually go do it.
Semantically, it feels like because object write operations are already kind of blind. You can't get back. We're already restricting it so that it can't be a read
pass or fail.
You can't get read information back. So I think you're right.
Now it would be super cool if you.
So the client actually would specify a master. Is that so that?
Sorry, go ahead.
What's that?
Yes. So you would. So the client specifies a master.
Why are we allowing the client to select a master?
Because often these transactions are like, write this 4 meg object and update this, 200 byte pointer to this object. And in that case, we want to send the master to the place where the 4 meg goes. Yeah, we want to avoid the double write on the master and also avoid sending that data over the wire. So in both cases, the coordinator, if it's doing the biggest piece of work, is sort of the most efficient. Then the 2-phase commit is happening on the little pieces. Now the downside of this is that we introduce the possibility of deadlock.
No, that's not right. There's a 2-phase commit on the. There's a 2-phase commit on the master too.
No, because it's in memory. It doesn't actually write anything to disk until it gets all the prepare acts, and then it commits.
That seems like cheating. Hang on. That you can do that as long as you don't. You can do that as long as you don't respond with success to the client when you get the prepares back.
Why not? Why can't you reply then too? That's your roll forward, roll back point when you commit.
Because because one member of the quorum hasn't actually persisted the prepare. So if you go through an interval change in the primary at that time, you'll get a rollback.
Oh, sorry. Yeah. So at that point, it can commit, and as soon as it finishes committing, then it would reply. So once persisted, the master sends.
That's right. But if the primary also prepares, that's right. But if the primary also prepares, then once everyone's prepared, you're good to go.
Right, but it doesn't need to. Oh, I see. So you could pipeline it.
I'm saying you're right, but you're paying an additional round.
Yeah. I see. Okay.
Or you're paying an additional dependent operation.
Additional latency. Yeah. But the thing you save is that you don't have to do two operations.
It might be worth it.
Because you don't have to worry about being able to roll back.
That's true.
So
yeah,
maybe you want to
you're
do both
right.
variants.
If it's the 4 megabyte case where you're creating an object, then maybe we can optimize that case and not do a double write.
Mm-hmm.
Because the prepare would say, I have written to this object, and the rollback is deleted.
Yeah. But that one always.
So if you're worried specifically about the case where you're creating an object and also updating a pointer, then we can get that one while still doing the prepare. If you're worried about a 4 megabyte overwrite, though, you're right. We would have to do it that way. I'm not sure if 4 megabyte overwrite is that common.
Yeah, me either. But I think it's generally not going to be the case that it's trivial to roll back.
No, it won't be. But in those cases, so in those cases, perhaps the cases where it is not a 4 megabyte new object, it is not a problem to do the prepare journal ahead approach on the primary and save the latency.
Yeah. Well, you could,
anyway,
you could do both.
choice.
You could do both variants. Probably wouldn't want to implement two variations of the same thing the first time through. Just pick one and do the other later.
Well, is there any issue with you want to prepare in an order? Do you want to prepare in an order so that you don't deadlock?
Yeah. So
therefore, the master and the slave should all be
but it also
equal
multiplies
peers.
the latency.
Yeah. Well, even just if the master were
so
always.
You can prepare an order, but it costs you latency.
Yeah. Or you can make the master always the lowest sorting object or something. That would also force a lock ordering effectively.
But who can guarantee that?
You can make Rados do that, but I think in practice it's because if you have a prepare on something, you would block until
that would only work if there were
back.
only.
It's the same as acquiring.
That would only
locks.
work if there were only two objects in the transaction, right? If there are n objects in the transaction, then yeah, the primary is the last one, and that one won't block. But the other n of them, since you submitted the prepares in order,
oh, you're right.
Parallel,
yeah.
You have,
you have to
no
guarantee
one
at a time.
that.
Yeah. Okay.
You actually have to do it one at a time, which is probably not acceptable.
Yeah. So maybe the simplest thing would be.
Also, it means that whoever you grabbed first is reblocked for a long time.
Mm-hmm. Yeah.
I'm assuming you're blocking reads between the prepare and the commit.
I think that would be an option because sometimes you don't care if people are reading the things while the transaction's happening. You just want to make sure that they both sort of persist
if you
atomically.
Give people,
you don't need the C part of assay,
correct,
I guess.
But if you
only need the.
That's true, but if you give people the option to use the wrong consistency semantics, they will.
They will. Yeah.
I get your point, though. It'd be nice if we could have our cake and eat it too, though.
I think.
in
I
that
mean, it would just
particular
it'd just
situation.
kind of be a flag whether
The
you
only
just
thing
allow
we have
reads.
to do is detect or avoid deadlocks.
Yeah, I think that's the hard part. So I mean, the
Yeah, I know.
we could cheat and just say that's up to the client to do that. I mean, in practice, like Rados Gateway is sort of the motivating example here. The master is always going to be the head object, or maybe not the head object, but one of the objects in an RGW object, like a shadow or whatever, and the index is always going to be a secondary thing. And there's never really a combination in which you would end up deadlocking because you don't have the sort of weird dependencies. But that's kind of dangerous. That's getting.
I mean, we could push that to the client. We could have them submit a list of. The interface could force them to submit an ordered list of object write operations of pair H object T object write operation, such that they promise that no two clients will submit operations with flipped or cyclic orderings.
Mm-hmm.
That is, it's a DAG.
Yeah.
That's not an unreasonable approach, but it's also hard to use correctly.
Yeah. Yep.
It also prevents them from having any kind of parallelism. So if we wanted there to be parallelism, for example, the case where you're creating n new objects which are necessarily at the bottom of the lock hierarchy because no one else can possibly be looking at them, then you'd want to be able to say you can acquire all of these locks in parallel and then acquire this one after.
Mm-hmm.
Which
so
is a more expressive interface, but that gets even harder to use correctly.
It seems to me like deadlock detection might be a simpler path here. So what if both the master and all of the prepares have a list of all the objects that are involved in the transaction, and if while a prepare or a master coordinator is in flight, we see another transaction that
I think perhaps your headset battery died, if you can still hear us. Or something. Or maybe I disconnected? Can anyone else hear me?
Yeah, I can hear you.
Yeah, I hear you.
Yeah. Sorry, it's the Blue Jeans likes to adjust my microphone volume. Sorry. So I'm not sure where I was. If
you cut out just after, I think deadlock detection is a good idea.
Okay. I explained the perfect solution. No. Okay. So if it feels like intuitively this might be enough information, but I'm not sure. So if the master obviously has a list of all the objects that are involved, if all the prepares also have a complete list of the objects that are involved in the operation, then if a second transaction comes along while the first one is in progress, we should be able to look at those two sets of objects that are involved and tell whether they conflict. Right?
I think that detects a size 2 cycle, but not a size 3 cycle.
Okay.
You could be blocked. So you could be sending you could be doing a transaction A and C, and you would encounter a transaction that is happening on B and C, which, as far as you know, isn't a problem. But there's a third transaction on A and B that you don't know.
Right,
about.
but you have all the information to follow that and find the loop.
You do if you're willing to send a whole bunch of messages.
Yeah.
To the other primaries.
Oh no.
Huh?
No, because everybody knows every object involved, and then everybody on a prepare can check the entire
but the problem is that
loop.
So let's say there are three transactions. One is happening on objects A and B, another is happening on B and C, and another is happening on A and C. Those three OSDs, any one of them only sees operations on 2 objects. Each one of those sees 2 operations on 3 objects that don't conflict, or rather that don't form a loop. The only way they would be able to form a loop, to detect that there is a loop, is that all 3 of them would have to get together and agree, even though all 3 of them are not in the same transaction.
Mm-hmm.
Yep.
Yeah, that's the hard part.
That's the problem. Yep. What is
Pushing this to the client is actually a pretty good solution.
Yeah, solution. I like. Yeah, I would.
No,
I'm not sure
really,
if solution
because
is the right.
no, because okay, so on the application, so if you're doing deadlock detection or avoidance, you have to solve the general version of this problem, which is super hard. Whereas the general version of this problem, where you have arbitrary cycles, hardly ever happens.
Yeah,
RGW, for example, always knows that there are only two objects ever involved in one of these transactions: a new object which can't conflict with anyone, and an index, and that's going to be true a lot of the time.
Yep.
And they can construct some kind of hilariously complicated watch notify lock passing system to do their own deadlock avoidance.
Yep.
That's not a good idea.
It'd be hilarious though.
So the other option is some kind of a timeout approach where you have some kind of exponential backoff. That's the detection. Well, that's the poor man's
avoidance
detection one, but that's not really a good solution either.
Yeah. Well, we could do it anyway.
Well, it's not avoidance. Avoidance is the one where the client arranges for it not to be a problem, right?
Yeah. Yep. Well, I mean, you could put a timeout in there, so that it'll just sort of, the master will give up after a while.
Yeah,
but whatever.
It's really unsatisfying though, because you can still get.
Yeah. Well, okay. So there are a couple other.
There really is no way to do action.
So there are a couple of other things here. Lovely details. So the first question is, where do we put the prepared transactions? My initial instinct is to put them in the PG meta object, because that's with the whip temp branch when and if that merges. That's sort of the only place that lives within the placement group, but is outside of the namespace that persists across, or can persist across pairing intervals. The temp directory gets zapped all the time.
I thought we created a whole temp. Oh,
yes, but it gets zapped. Yeah. So that's fine.
Yeah,
I think
right.
I think the way that we construct this, it would be fine to put the transaction in an OMAP key in a nice little slot on that object. I think that would work just fine. If you have a really big transaction, then I think it's your own fault if it's kind of slow. It's only happening on the slaves and not on the master.
Yeah, I don't know about that, because you could have multi-megabyte writes, and that's not even a bad thing, right?
It's not, as long as it's not the master. But if it's the slave, like, are you going to have multi-megabyte writes on two objects that you need to do atomically?
Possibly. I mean, that doesn't strike me as a particularly awkward thing. Like, if you're looking at the Liberatus interface and you're like, oh, looky, I have atomic operations. I would like to atomically update these two 1 megabyte chunks in these two objects, because that's where I can't think of anything, but something.
Yeah. Well, okay. Well, I think either way.
Anyway,
it's
not. That's not such a big problem.
The awkward part is that these need to persist across pairing intervals, because we did a prepare act. We promised that they're persisted, which means that they need to be captured by recovery, which means that we need to put something in the PG log.
These need to be internal objects. No, these need to be rep ups.
Yeah, absolutely. But would they go in
the? These need to be in the internal namespace next to hit sets.
Okay.
These need to. These should be handled the way hit sets are. We can make an even more internal namespace.
No, I think putting them next to
strictly speaking, hit set objects are accessible through Liberatus. Mm-hmm. But yeah, these actually shouldn't go on the PG meta object, because they're replicated and everything.
Right. Yeah. Okay. Yeah, you're right. Okay. No, put them in internal.
In which case
it's just a rep up, it's there's going to be a PG log item, a special PG thing called prepare that is associated with that internal object and has some stuff. When you load it in though, you'll need to load up the object context on the actual object that you're preparing against, so you can update its lock state, so that when a read comes along, you block, that sort of thing, and also so that when peering completes, it'll send the notify back to the master that says roll forward or roll back. And then you need another entry that's the actual update, which I think is just a standard update on the actual target object, and is committed along with an entry with type delete on the internal prepare object. And we'll just put those, you'll just do those two log entries at the same time, similar to what we do with clones, where we just have two log entries. We just happen to do them together all the time.
Yep, seems too small.
Okay. Okay. Are there any other problems?
Actually, just as a brief sanity check, does this fully handle the Radius GW use case?
This sounds remarkably like the conversation we had like a year and a half ago when we were first talking about this. I think that the Radius GW one is like a series of, it's like a 5-phase or 3-phase type thing, where there's it's like object index or something like that. So it's actually like 2 transactions in sequence.
Oh, right, because there's the garbage collection thing and the atomic switchover of, oh yeah, okay.
Yeah.
So maybe, but it would probably look like 2 transactions, not one.
I think it'll be 2 transactions, yeah.
Okay, so it's not really appropriate anyway.
Yep, but I think there are a bunch of cases like
I forgot about that,
where it would capture that, like in all the garbage collection maybe, or something. I don't know.
Yeah. No, it's fine. Like, I just wanted there to be one thing where it was like, yes, that just handles it.
Yeah.
So right, because Radius GW, there's the thing where it has to start the upload process and like reserve itself a number or something. Then it has to actually write the multi-part upload out, and then it commits it. And yeah, those things are separated in time.
Yeah. Yep.
Was that it? Anyway.
I think so. Yeah. We got a couple questions. Yeah. Okay.
So what other use cases do we have in mind for this?
In RBD land,
that it would be much easier. A sharded Radius GW bucket would be a lot easier.
Yeah.
Oh, read transactions are a component to this.
Yeah, I was just going to ask about that. You've been all talking about writes.
That's actually moderately important.
Consistent reads too.
Yeah, because if you want to do something like create a multi-object distributed ordered key value thing, you probably want consistent reads too. How much of this just works? It kind of just works.
Does.
The primary
you just don't have to persist anything, right? You just have to do the locking, but you still have a coordinator.
Yeah.
Yeah.
The primary just acts as a proxy for you. Yeah. It's no big deal.
Exactly.
Right?
Yep. And while the slaves are doing their reads, it's but it actually needs to quiesce all of them and then read all of them.
You still have to send preparers, then send the actual read.
Yeah, so it's like more phases.
Not
unless there are only 2 objects
in this world, but it's the same concept.
It's lock, unlock, I guess. Lock, release.
It would also be nice if you could do the reads in parallel if there are multiple reads. transactions at the same time, which might be a bit harder, but doable, probably.
That one actually is comparatively simple. Because the prepare part, the read variant of prepare actually just takes a read lock and holds it until either the transaction times out or, well, no, it doesn't time out, until you hear from you get a cancel from the primary.
Okay. Yeah, that makes sense.
Actually, maybe it just times out when the primary goes through an interval change. That actually is easy. It can just time out when the primary goes through an interval change, which the other replicas always know because they have OSD maps. That's nice. Sort of.
Yeah.
In fact, they know when any of the other PGs go through an interval change. Everyone does.
Yeah. Yep. Yep.
Clear about the semantics here. When something gets rolled back or times out, that's if it goes back to the Rados client as some kind of error, like E again, and they retry with a new operation.
No. The client, the objector just gets so it would just look like the objector knows all of the OSDs involved in the transaction replica, or all of the placement groups involved, and if any of them go through an acting set change, it resends it because it knows that if any of the primaries for those placement groups see an interval change for any of the other primaries, they will assume that the transaction canceled.
On a read transaction or a write transaction?
Visible. It's just that we don't need to do anything like with the writes. On the read. The write one is more complicated because we might roll forward.
Because it's persisted, yeah. I think in that case
we don't know if the clients have already gotten a success.
Yeah. I think in the case of the
you could be cleverer, but you could make it as simple as if anything happened to any of the placement groups, we just give up and try again.
Yeah.
I mean, we could do that with regular Rados ops. We just don't because we have an optimization for it.
Right.
Where if the primary didn't change, we keep the op.
Yeah. Where I think the same behavior actually works just fine because the coordinator can say it sent 2 prepares and got 2 prepare acts, and the third one had an interval change. It would just resend that one piece.
Yeah, that's the part that seems complicated to me, but I think you're right. It's not that bad. Anyway, it's conceptually simple.
Yeah.
Since everyone has the OSD maps.
I mean, Josh, wouldn't this help with like the bitmap updates, for example?
Well, with those, we kind of already have like. I mean, it would help in that it would give us more guarantees of adamantly there, and it would be simpler to program to, but it's also a lot of extra writes to do it.
And we don't actually care about the consistency in that case. Yeah. Or what was the other thing? It was like the locking metadata is stored on both the bitmap object and on the header.
Well, there's a separate locks for one for updating the header and one for updating the object map, just for extra guarantees. But yeah, so we could certainly try using this, and if it doesn't add a lot more latency, then it would certainly simplify things with not having to have those extra locks on the object map. One other thing that is immediately in my mind is the possibility of having O-atomic in the future for SuffFS. If that gets implemented in Linux, this would be a really nice, easy way to do that in SuffFS.
Sorry, remind me what O-atomic does.
It's basically guarantees you atomic writes, I think, to a memory mapped file that's used by one process.
So when you close it, it all
when you close it, it atomically makes all those writes persistent.
I see. Yeah, it would be order. It would be a transaction of size order n, which would be kind of
right.
complicated, but Yep. Oh, you know what it would also give us is
Whoa! You mean it opens an M-mapped region? You are allowed to make changes to it, and when you close it, it atomically changes it to whatever you change the M-map region to?
Yep.
basically like all the pages that you dirtied get sort of
That's a
atomically
nightmare.
collapsed onto the. Yeah. Go figure. It's an order in operation, which is sort of tricky. So the other thing though that
yeah,
is
that
really
doesn't
simple
fit with this model.
is just that in POSIX the writes are supposed to be atomic, but we break that when we cross stripe boundaries.
Oh yeah.
FFS.
Mhm.
So that would do that pretty simply when you're in read-write mode.
You and every other file system.
Yeah. Yep. It would make the B-tree stuff actually work much simpler, much more simply. I think the interesting thing is that in almost all of these cases, you actually don't want the exclusion. Like you want to allow reads while the transaction's in flight. It's actually just the cleanup that we care about.
It should also be noted that in almost all of these cases, we already have incredibly carefully tuned protocols of our own, and that therefore they are not representative.
Yeah, I think it's probably this is
I would
more
argue
useful
that
for
these
things that
are,
don't exist yet
almost
because
the worst
they don't make
possible
sense for the existing
examples.
Rails things.
I think you guys both said the same thing.
Well, because they're too difficult to implement with Rados right now.
Yeah.
I mean, our existing use cases are things that are designed on top of Liberados with its limitations in mind that also need good performance. This is more for applications that are not currently written for Liberados because it's too hard.
Yeah.
Which is frustrating because we don't have good examples of those.
Yeah. Yep. Okay.
Although if we could get, I mean, there is already an example in the tree of a sort of splitting B tree implementation on top of Liberados. So one exercise might be to take that design and work out how much easier it would have been if she'd had access to transactions.
Yeah.
That might be worthwhile.
Did Lee ever show up? He's connected, but not here. Yeah. Okay. Okay. So I mean, I think we agree this would be useful. It's also not at the top of the list of things to do.
Hard.
It's hard, but not so hard.
It might be useful in the future for making something like a log structure.
Not conceptually difficult, but this is
doing garbage collection and that kind of thing atomically. I don't know.
Yeah.
Updating metadata across objects.
See, my worry is that for applications like that, you'd want to relax the atomicity guarantees so that you can get acceptable performance. So we need an example of something where the atomicity guarantees here are actually completely necessary. Because with the log structured file system thing, half the advantage of a log structured thing is that you can elide the end of the log if it turns out to have been inconsistently applied.
Mm-hmm.
Since the log grows one single object at a time. So that seems like it would be ripe for a strategy where you don't actually need multi-object atomicity.
Yeah.
Not that it would be easier, or not that it wouldn't be easier to do with transactions, but it might be slower.
Yeah, I wouldn't think that like the generic writing to the log would use transactions, but some kind of background garbage collection type operations, or repacking data, or that kind of thing. We actually want to repack data atomically into new objects and still have the old data around until you get rid of it. I don't know. Maybe it's not necessary.
That's true.
Okay.
that all we wrote for
I
this one?
think we might be all she wrote.
Okay, outstanding.